This demonstration shows how to use the WaveAnalyzer as a high-precision wavelength meter. To open the wavelength meter capability, click on the Wavelength Meter button in the Analysis tile. This opens up the wavelength meter table, which shows the peaks identified and the power in each of those peaks. The region that the system is measuring over is defined by dragging these sliders here to increase or decrease the wavelength range or frequency range identified. And each of the peaks is numbered, and that number corresponds to the line in the table. The identification of peaks is done automatically using the embedded wavelength meter software within the WaveAnalyzer, but for more control, it's possible to adjust these settings by clicking on the Settings button over here. This opens up a subsidiary window where you can set various parameters of the measurement. The top section, the analysis range, you can select either windowed as we show here, or it's possible to run this across a full scan. The second section, entitled Calculation, allows you to define how the peaks are calculated and the way that the power within that peak is calculated. So the calculation type default value is moments, as that is the most robust method of identifying the centroid of a peak. But it is also possible to use just a simple peak find approach. For the power measurement, you have to define the wavelength range or frequency range over which the power is integrated. Default for the WaveAnalyzer 1500 is 150 megahertz, but you can set this up to be anything up to 25 gigahertz to allow you to measure the power within that peak. And finally here, the peak algorithm. This is the way that we define what is a peak within the measurement of the system. And there are two parts of this. One is a threshold power, which is the minimum value that the software will consider investigating as to whether it's a peak. And this should be set well above the noise floor of the instrument to avoid any false peaks being identified. And the second one of these is the excursion. That is how far above that threshold power does a value have to be a valid peak. And we'll just show a demonstration here of how changing these values affects what is defined as a valid peak. So at the moment, the threshold power has been set by the instrument during its auto-seek process as minus 44 dBm, and the excursion is 7 dB. And what you can see from that is that there are a number of subsidiary peaks that have been identified here, which are basically sidebands of the main signals, and we don't want to have these identified as wavelength peaks. So we're going to vary the threshold power and the excursion to understand how these affect those values. So first of all, what we're going to do is we're going to take the threshold power down from the current minus 44 dBm, and we'll take that down to minus 54 dBm. And what you can see now is that this generates a lot of subsidiary peaks, that value is basically too low, and we've generated all of these additional peaks down here which are wrongly identified as wavelength peaks. So what we'll do is we'll put that back up to the original 44. And we still now want to get rid of those subsidiary peaks. So what we're going to say is that we now need to have a higher excursion from the threshold to remove those subsidiary peaks that we don't. So we'll just increment the excursion that's required to define how big that excursion has to be. And you see what we do is we say, as we increase the degree of excursion, the number of subsidiary peaks reduces because they're not going high enough above the threshold power. And at this point, we've got an excursion of 18 dBs above 44 dB, so that means that the signal must be over minus 26 dBm to be seen as a valid peak. and we now just have the main peaks identified here. So you can vary these parameters in any way that you like. At any time you can rerun the peak detect software by clicking on the auto detect button to take you back to where you were previously. At any time, if you get lost in here, there's the help button, which pops up a window which just explains the meaning of all of these controls. And you can also save the measured frequency table by clicking on the Save button, and this saves the data in the WaveAnalyzer export directory. It time and date stamps every measurement so that you get basically a unique identifier for each measurement. In summary, the WaveAnalyzer can be used as a multi-peak wavelength meter. It can find up to 2,000 peaks per trace, and by using the settings of the wavelength meter capability, you can vary the way that those peaks are calculated to match the measurement requirements that you have.